Hey team, I'm Maddie. Welcome to Science Side Up, and today we are talking about dry adiabatic lapse rate. Dry adiabatic lapse rate. There's some pieces there, so let's break it down. We're gonna start with what is lapse rate, and then we'll add on the dry and the adiabatic components. Lapse rate's pretty simple. It's just how does temperature change with height. If my temperature profile in the atmosphere looks something like this, with temperature increasing to the right on my x-axis and height increasing up on my y-axis, then a normal temperature profile in our atmosphere would look something like this. Just decreasing as we go up in height. The lapse rate in this imaginary atmosphere is just the slope of this line. Even though this line has a negative slope, this has a positive lapse rate. Why is it defined that way? Because whoever defined it thought that was a good idea and it became the convention in the field. And one more note, the less I decrease with height, boop, 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 the lower my lapse rate is. So my solid line here, that represents a large lapse rate, and this dotted line is a small lapse rate because temperature didn't change as much with height. So when I say slope, it's really better to think of that as flipping your axes because it's dt dz. And normally when we would read slope like this, it would be d z dt. Anywho, how steep this line is, that's what we're thinking about. That's what a lapse rate is. Now let's think about that dry adiabatic portion. So before we get into those specific definitions, conceptually, the dry adiabatic lapse rate is going to be a reference value. It's not representing like real changes in the atmosphere. It's not a lapse rate we would ever expect the atmosphere to really follow, at least not for very long, but it's a good reference state that we can compare other things to. The dry and dry adiabatic lapse rate just means that we're gonna assume that there is no water vapor in our air parcel. So in the air that's changing like this, no water vapor, fully dry. And we know that that simplifies our life quite a bit. And then the second portion, adiabatic. I've got a video up on what does adiabatic mean, but adiabatic changes in temperature are just going to be changes in temperature due to the change in pressure with height determined by our ideal gas law. So this air parcel isn't being heated or cooled by the environment. It's just changing temperature because of those changes in pressure. For our own sanity, here's our ideal gas law. If pressure is decreasing, temperature better also decrease to keep this whole equation balanced for constant density, and obviously the gas constant is a constant. Putting all of that together, the dry adiabatic lapse rate is how fast the temperature of an air parcel changes with height if that air parcel has no water vapor in it and its temperature only changes because of the change in pressure. I'm not gonna derive the expression for dry adiabatic lapse rate today. My favorite way to get at it involves some thermodynamic calculations, and we haven't learned those equations yet. But I will go ahead and give you the final answer. Dry adiabatic lapse rate, represented by this capital gamma subscript d, so that we know that it's the dry one. This is gonna equal acceleration due to gravity, 9.8 meters per second squared, divided by Cp. Cp is specific heat capacity of dry air at a constant pressure, and that is 1004 joules per kilogram Kelvin. If we just divide this out, we'll get a lapse rate of about 9.8 like degrees Celsius per kilometer, we usually just gonna round that to 10. So we're gonna call the slope of our dry adiabatic lapse rate, we're gonna call this 10 degrees Celsius per kilometer. And that's my dry adiabatic lapse rate. Okay, team, that's all I've got for you today. I hope you liked this video, and I will see you all in the next one. Bye, team. This is 1004 joules. Oh no, joules per kilogram or joules per Kelvin? Oh, notes.